Can start. Hello everyone, thanks for coming. So our seminar speaker today is Beatriz Villarroel. She's from Sweden, even though you can be confused because of the surname, although she's learning Spanish. So Beatriz did her PhD at the Uppsala University in Sweden, and she got her PhD 2 years ago. And then she spent some more time in Uppsala, and then she got a grant from the Swedish Research Council. I think it's called a Nordic fellowship. So she's based at the Nordita Institute, but also she has to spend 2/3 of her research time in another institution abroad. So he chose the IAC, and she joined my group in last year. So in principle, she's going to be here in and out, sharing with Nordita for the next 2 years, because she has been already 1 year here. And today she's going to present her recently accepted work on, well, the first paper of this project, the VASCO project, and she will tell us about it. Thank you.
So, we humans have, as long as we know, been staring up the sky and been wondering about why we are here, who we are, and try to understand our place in this universe, or in the world, or how one. Sorry. And with the development of technologies that allows us to watch the universe and observe billions of objects, we nowadays can actually study very well our place in this universe. And this brings us to even more important questions that we have been iterating over and over for the last decades, and that is whether we are the only civilization here, or if there are many more civilizations similar to humans or more advanced than just us. This has been a question that people have been approaching in so many different ways, through philosophy, science fiction movies, science fiction books. When one takes a beer in the evening with your friends, there are so many ways how we have been approaching this. We are simply fascinated. We have to admit that we are fascinated by the question whether there exist other civilizations than just the humans in our universe. One may wonder if this is a reasonable thing to assume or not. I think it is reasonable, let me argue. Well, we have billions of stars in the Milky Way. We have billions of galaxies in the observable universe. We already know there are so many Earth-like planets just in our galaxy. One estimates that like 5 to 50% of all stellar systems have Earth-like planets orbiting. If you try to estimate the number of Earth-like planets within the observable universe, you end up with a really large number, 10 in the power of 19, 10 in the power of 20, just those orbiting the FGK stars. One can also try to make some more speculative estimates and try to see what is the distance to the closest planet that could be hosting any form of life. You find 10 light years, and if you now try to do this for a super intelligent civilization, you might say, oh, a super intelligent civilization should be closer than just a few thousands of light years. Now, when we talk about super intelligent civilizations, we mean something much smarter than ourselves, which is something that not only can harvest the richness on their planet, but also harvest the star or many stars in the galaxy, or potentially just spread all over the universe. So now, if there are so good probabilities just from numbers to find life, even although we cannot know what are the necessary conditions yet, because we only have ourselves to study, Fermi asked a question: if there are so many possibilities for life to exist in our universe, Why haven't we found them yet? Where is everybody? This is known as the well-known Fermi's paradox. Now there are a couple of solutions to the Fermi's paradox. Maybe intelligent life doesn't really exist. Maybe we're the smartest in the whole universe, and maybe we're not even smart ourselves. Maybe maybe the universe is totally full of life, but we can't, and we cannot, and will be able to find each other. The distances are too large. Maybe we never exist at the same time as some other civilization. It's also possible that life is a very, very short period, or has a very, very short period, and maybe we always extinguish ourselves before we manage to reach out or colonize some other planets. And then there is, of course, one can go to a little bit more religious ideas. And then one can also take the Fermi's paradox the simplest way, that maybe the question wasn't really well timed. Not every question has a sense, and possibly that is it's true about Fermi's paradox as well. Maybe it just takes time to discover things. Well, the searching strategies are three. The first is the direct detection. Imagine you could look for, you would actually go to Mars, you would send there, some robot that would be walking around, taking samples, taking photos, and then you encounter there a big animal. Now, I'm sure that it has been pretty difficult to miss in the news about the scientist at Ohio State University that claims that he has found some animals on Mars in photos. And this is what the photo represents. I cannot remember what is up and down. Oh, sorry. I think I clicked on the wrong thing. Do I do like this? So I cannot remember if this is an insect or a reptile or what it's supposed to be, what is up and down. And I think there were many more than me that struggled with seeing the insect on this image. But if you want to follow the news, and you can always read up on it. I am myself very, very skeptical to this. Then there are more promising, perhaps, ways of trying to detect life, and that is by looking at the exoplanet atmospheres. One can try to detect some typical signature of life in these atmospheres, and this is what people are now trying to develop techniques and instrumentation in order to do searches in exoplanet atmospheres. And the last one, the last way we have, which is not a direct detection by going somewhere or sending somewhere sending some robot somewhere, and neither is looking into exoplanet atmosphere. The last way is SETI, and that would actually be not to look at the signatures of the biology, but the signatures of the technological advancement of a civilization. Let's say you look for rest products from their technology. If they have interstellar wars, you look for rest products from these wars. Or if they have been doing some other interesting things. And maybe the most direct is that one tries to look for radio communication or some sort of signals that they could be emitting towards us, or subconsciously. Not subconsciously, unconsciously. So SETI is nowadays regarded a little bit as a not super serious topic, but actually in the 50s and 60s there were a number of nature and science papers related to SETI when we were proposing, let's look in radio, let's look for laser communication. And these are just two screenshots I took from these papers. I think when most of us think of SETI, we are thinking back at the radio SETI. We imagine now, for us who have seen the movie Contact, we remember this astronomer who was watching, listening to, with her headphones, and hoping to hear ET. Well, the most traditional way is, of course, to point your radio telescope on a star and studying the star for a long period, hoping to hear something there. And, of course, if you find something, you will be very happy. This is the most accurate way we have, in case we would find something currently, or maybe one of the most accurate ways. The problem, of course, is that there is a lot of, one usually mixes up these signals with a lot of Earth things, like, let's say, satellites, and if you have a Roomba robot, could also give some signatures that can be confusable with ET. So there's a lot of contamination that one struggles with. However, it would be very, very neat if one could detect ET this way. And at least follow-up observations are always well done. Problem is that we don't know what are the typical frequencies ET would emit with, nor the occurrence rates of the potential transmitters. We simply don't know anything. And when I was working on going through the parameter space and like currently like searching in different wavelength regions and looking for it and trying to see where do we have something and where don't we have something, one hasn't found anything yet so far. Ah, yes, sorry. The most famous, I think, example of when people thought that we had found something was the WOW signal that happened in 1977. It was 72 seconds long. It was this typical strong narrowband signal, just exactly as one expects ET emitting. It came from Sagittarius, and it never repeated again. Simply, it never repeated again. And of course, we know that things have to be, one needs to be able to confirm any prediction or any observation. So is it bad or good that people are excited about aliens? Well, I here make an example of when one discovered the pulsars. One of the first thoughts was, is it little green men? And it led to a very interesting discovery by Jocelyn Bell. And of course, it turned out not to be any little green men, but this thinking, is it aliens, might be a bit of a driving force, I would argue. Another example of where people very enthusiastically, with even greater enthusiasm, ask, is it aliens, is the Oumuamua object. And that was discovered in 2017, which is this long cigar-shaped object that is rather red. And so what happened? People then thought, oh, this is maybe, it's so, the form is weird, we cannot observe any gas from it, and it doesn't have any tail. It looks like a rocket. And there went a lot of speculations in the media. Also, fast radio bursts are watched through the same lens of the aliens. And here it has been hypothesized that some of these repeating fast radio bursts that come from the same place may be light sails causing them, sort of artificial constructions. Although I think more and more natural explanations for both the phenomena are emerging as they're getting better studied, and I think the alien idea is vanishing more and more. But still, the question, is it aliens, seems to have been a driving force for doing better examination of these objects. Some years ago, I think it was 2015 or 2016, I cannot remember, the breakthrough listen program was initiated, and that happened when a Russian oligarch, Yuri Milner, donated $100 million to do SETI research. And they started with 3 major telescopes, the Green Bank, the Parkes, the Automated Planet Finder, and then they have now expanded to using many, many more telescopes over the whole world, hoping to find ET. So what they hope to do is to search for laser signals and radio communication from 1 million of stars and 100 more galaxies, and they also are going to point at the galactic center and try to study it very well. And this is a very, very serious program, and they are doing the most fundamental SETI research today, together with the SETI Institute. So, has anything been found yet? I make here an example of different optical SETI studies one has been doing. For instance, when one has tried to look for, like looking into the spectra of 5,600 stars, hoping to find laser emission there. No, nothing has been found so far, and one has tried to set some sort of upper limits. And currently, it's the problem with these upper limits is that sometimes if you try to look through a very, very large volume, you restrict yourself to also, the way how you have to handle this is by restricting yourself to only the strongest signals. And here is an example of where they try to look at the length of, basically the length of an optical laser, how long this pulse will be, and try to look at the fractions of stars that are that could be hosting this sort of, or could be transmitting, and they find that no, we don't find anything, we don't find anything. And I think one of the upper limits is set is like 10 up to 10 in the power of -7 as a fraction. It's simply, so far nothing has been found, neither if you look for continuous or pulsed optical lasers. And this is how it looks. We have nothing in radio so far and nothing from the optical searchers. There's also another way today to do SETI, and that is by doing SETI with large databases. And we call it artifact SETI very often, because one tries to look for some typical artifacts. What are the typical artifacts? I will say the most famous is maybe Dyson spheres. If you imagine a giant solar cell that is encompassing a star, and you basically harvest all the energy of the star, and out comes only waste heat, and you have infrared as a possible signature. So has anyone been looking for stars or galaxies with infrared excess? Well, there have been a number of studies. I only list a few, and the first one was in 1991. Yugako and Nishimura, they look at something like 550 objects, and they find that no, there is nothing that seems to be a star with a Dyson sphere. This has been later repeated, 11,000 sources. No, they find nothing. Then also Zachrisson et al., they try to look through 230 stars with the Gaia DR1 and the Rave DR5 by searching for objects that are less luminous than what they should be, and they find nothing. So far, no Dyson sphere candidates have been found from these searches. Another way of approaching it is by looking for outliers and anomalies. Now, there was this project called Planet Finder that maybe weren't out specifically for looking for ET, but in this Planet Hunter project, people were trying to look at the light curves in order to try to detect some interesting exoplanets and so on, and they discovered the Tabis star, which is a star that has some very weird and unusual light fluctuations, and also it seems to have dimmed like 20% over the last century, which has made a lot of people very, very keen on trying to understand what is happening here. If it's a very young stellar system, or if it is some comets that are fragmenting, or if it's some dust layer. And it's a very popular object to study. And of course, you cannot avoid that people have been trying to explain the weird light fluctuations by saying that there might be a megastructure in front of it. Although this doesn't really seem to be the case. After that, one has done even more follow-up work. One has, for instance, tried to point the radio telescopes on it, also to look for the lasers. Nothing comes out of it, and it doesn't seem to be any artificial megastructure either. We also proposed a different way in a previous publication, that instead of looking for something directly anomalous or so, one can try to set a filter. Let's say we look for something that would be just not physically possible in our data. Because if it's not physically possible, it shouldn't be real. And when I mean this, let's take some absolutely absurd examples just to illustrate it. Imagine now a galaxy growing to double its size over half a year. If I would find that that a galaxy has grown to double of its size between Sloan and PanStarrs, I'd get worried. I don't know if you would be, but I would be slightly worried, or get intrigued at least. And we proposed also here that physically vanishing stars or galaxy could be something interesting to look for. And of course, one would, if you look for impossible effects or impossible things, this is going to be confusable with instrumental errors and instrumental, but also possibly maybe some of the fundamental ideas one is posing could be wrong, turn out to be wrong. It doesn't need to be aliens, of course. But the point is that by looking for something that is slightly more absurd, one could either find new astrophysical phenomena or maybe detect good ET candidates. We did it, and the result was that a creationist website that prayed for us very strongly. We got a lot of prayers that I'm very thankful for. We didn't find particularly much in a pilot study when we tried this. And what did we do here? Well, we used the US Naval Observatory catalog, and we used 10 million objects from there that had no proper motion, and tried to look for if something had disappeared in the SDSS. Now, the USNO catalog is from the 1950s. So it was before one, it is from the 1950s. And SDSS, I think, is from 2000 plus, and goes like 3 magnitudes deeper. Did we find something? Well, we found one sad candidate that was supposed to have 2 detections in POS in the first Palomar survey and also in the second Palomar survey. Now I'm going to try the laser here. Which button is it? This one? Ah, yes. So we have this thing in the 1950s that wasn't seen later in the 2000s, and it never resurfaced again. Simply, it was seen only once, and also in the POS2 there was a detection, and then never again. Now, the USNO catalog has a requirement that each object that is included in the USNO needs to be detected in at least 2 different epochs, which was the neat thing why we chose it. So we were wondering, of course, is it a missing object? And it was very faint. We couldn't find it in any modern archives. We looked through SDSS, Gaia, PanStarrs, WISE. It was totally lost. And it was far too faint to be detected by all the archives, like you can find at Sonderberg Observatory, because they don't go that deep. And we also discarded later the second detection. We just thought it didn't seem particularly real. So we did follow-up observations with a knot, and it seems that there is actually something there at the spot where it was supposed to be. Like 1.4 arc seconds away, and there is an object. There is actually one more slightly further away, 2.4, but yeah, I think I'm shaking a little bit too much to point it precisely. But there is something there, and if it's the same thing, which we think it probably is, then there's a drop of 4.5 magnitudes, which is quite neat. So it could be, so we can't say what it is, of course. We can only see it in the red band. We haven't done any blue observation yet with a knot. But it could potentially have been that in the 1950s some supernova went off in a background galaxy and we happened to catch it, which wouldn't be the most exciting discovery on the planet, but interesting enough for us. Possibly it could also be some variable star. We don't know yet. We need to do more follow-up. So, and this is what we actually are doing with the current project. This is, instead of looking at this, instead of continuing with only one object, we have decided to go through the entire USNO catalog and cross-match it entirely with PanStarrs, and we have done that. And so what, is the interesting thing when you cross-match catalogues this way. First, you have a 70 years of time window for variability. During the 70 years, you can catch a lot of things that happen on a short time scale, but also things that happened slowly. Because most surveys today, like IPTF, they have maybe 5 years of data, or just have a few years of data. Stripe 82 might have, I don't know, also 5 years of data. While we want to look at a phenomena that happen over these 70 years. First, if you have something that only happens once every 100 years in the Milky Way, you can catch it. And second, the longer time window might open up for new phenomena to be found. And we, for instance, like vanishing stars. And vanishing stars might sound very science fiction, but they are actually a hypothesis that some supernova when a star collapses within 18 to 25 solar masses might not be luminous in the sense that these supernova are called failed supernova because the star directly collapses into a black hole instead of emitting something very, very bright. So these are some of the things that are hypothesized, but one hasn't confirmed the existence of these events yet. And potentially one would be able to find it in the Milky Way as well. And the goal of the project simply became to not only look for vanishing stars, but trying to explore a little bit this time window of the 70 years in the USNO and between the USNO and PanStarrs. So why are vanishing, what do we actually mean by vanishing objects? Well, there are two different ways of categorizing them. We can mean physically vanishing, that something was there and it's not there, and the second thing is observationally vanishing, that something becomes subluminous, that it simply falls beyond the detection limits. And here, I guess one will be able to find a lot of variable stars and also, I guess, a lot of AGN that have, for whatever reason, dimmed several magnitudes. Physically vanishing, as I mentioned, the failed supernova, when a star directly collapses into a black hole, that would be such an example. And then the new exotic physics and ET is, of course, the thing we are most interested in. So this is this is the goal. This would be nice if we would have managed to find it. As I mentioned, here's an example of a different paper by Adams et al. In 2016 when they were actually looking for this failed supernova. And you see a star is here, a star isn't there, they have two HSD images, but this is a star in a different galaxy where they have much higher star formation rates and much larger probability than in the Milky Way. We also calculated a little bit, we also calculated the probabilities to find a failed supernova in the Milky Way, and it's not a big chance unless the IMF is totally extreme. It's not a big chance. So what's most likely that we are going to collect in such a project when we compare USNO and PanStarrs? Well, everything possible in the variable space, sort of. Eta Carina is an example of an object that has had a very interesting light curve to study over long term. But for me, AGN are more interesting. And how could one kind of explain AGN that would vary, I don't know, 3 or 4 magnitudes over a couple of decades? Well, one has found a couple of AGN that has varied maybe 2 or 3, 2.5 at most. And one tries to understand what it is that causes this variability in this AGN that goes very slowly. These are not blazars. These are things where the variability happens slowly over 10 or 15 years. And one tries to understand it either through microlensing or that one maybe has some super luminous supernova happening in the accretion disk. Also, if there are possibly changes in the Eddington ratio. And these long-term variable AGN are quite interesting objects to study because they can give us a lot of information about AGN physics. So I wouldn't mind to find one of these. So, yeah, The challenge here is, of course, that we are going to have a lot of images to look through, because there's one thing to cross-match the data, and the second thing is to clean up from all the artifacts that exist in PanStarrs and USNO. And this is what our paper was about. We cross-matched 600 million of USNO objects with PanStarrs catalog. We must say we used an extremely generous cross-match radius. The advantage of using an extremely generous cross-match radius is that you implicitly take care of a big number of proper motion-related issues. And that's what we do with them. Well, we got 150,000 objects that existed in USNO that couldn't be found in PanStarrs, for all possible technical reasons, I would say. And what was the point of this? Well, in the initial data collection, before we start saying what is vanishing, what is not vanishing, what is what, so to say, among these candidates, you can find a lot of things that go there. And we have tried to hypothesize all the possible things that could be going into this initial candidate selection once you remove all the instrumental effects, because this is minus the instrumental errors. And, well, we are, of course, interested into this part of the picture more, hoping to find these ones where something that has existed in several images disappears, or that something does the opposite, appears, although we haven't actually looked for these cases yet. However, it's not impossible to catch communication lasers this way either, because one would see something that only would be observed in the red images. And, well, long-term variable objects probably are going to fall into the initial candidate selection as well once we have removed all these instrumental effects. And then maybe we will find some cataclysmic variables, and maybe we'll find some supernova. It's a lot of things that you can find in this initial initial candidate selection when you do it. And the trick later is to try to reconstruct the light curves, or try to constrain ourselves and try to classify the things we have. So first we took a look at the statistical properties of the sample. You find that these mismatches are different from the typical USNO objects. Even easier it is to see if you look at the color of these objects. You find that the typical mismatches, those that cannot be found in the PanStarrs, are quite red. They're quite red, and they have higher proper motion, which of course is natural, because a number of high proper motion objects might be lost in this, or might be caught up like candidates. So how can you actually solve it? Well, if you take large enough image frames, you can flip an image, like an old image and a new image. And if it's proper motion, you're going to see the same objects just in a different spot. So it's quite simple. Many of these objects are also redder. How does one do this? So in order to even more inspect them, we have visually examined 15% of these 150,000 candidates visually, which has been a painful, very painful process to do. And, one finds that a lot of these, of course, there are a lot of instrumental errors here, like that you get Sloan cannot detect an object near these bright stars, oversaturated stars, and a lot of things like that happen, or that something exists but Sloan just didn't detect it. And from these 23,000 images we had a remaining 1,600 of objects where we had to be comparing, that looked like there was something missing, and where one was comparing with the POS1 directly. Because when you compare slightly the POS1 the fields of stars in the POS1 with the Sloan, you can directly see if something has appeared or disappeared, and you're going to throw away a lot of things because you have so many instrumental errors here. And then plate defects is something you can also expect in the POS1 images. Now, nearly all plate defects are scratches, or they are big and ugly, or it's some small letter, or something like that. Nearly all plate defects can easily be detected. You just see it directly, like here something happened, or... I'm showing here examples of very unusual plate defects that were very rare, but that I still caught up. This one is not point-like. It has a little bit of a weird shape. You can see that. It's only seen in POS1. This is also one of the weird plate defects that seem to have been caught. Not stars, some blobs, 3 blobs next to each other. And here something seems to have been broken, like, or 2 different, like, a broken plate. And these are some of the most unusual plate defects we found. And then once we had, when we went down from 150,000 candidates, took the 50% of the subsample, this 23,000 images, we ended up with 1,600 things where we cleaned away all this type of both unusual plate defects and very obvious plate defects that are much more common. What did we find at the end? Well, we actually find 100 transients of some sort that seem to be very short, because if you observe it like 2 different images where one is taken 1 hour later, you only find it on one in many cases. And 1/3 of these transients are more than 5 magnitudes. And they are not cataclysmic stars. They are not some sort of variable stars, because if you have, as I mentioned, this kind of, when you look at them through different bands, you don't find them. They're not solar system objects either, because you would have seen with these speeds that, or these timescales that we have, it would have left a stripe, not a point source. They are unlikely to be plate flaws, because we did plate flaws tests, we measured their seeing, we compared to the seeing of typical stars. They seem to be real astronomical objects. Possibly, they might be the most ordinary M-dwarf flares, just very strong. So 1/3 of them, as I mentioned, have more than 5 magnitudes. And we are not coming up with an interpretation yet what it is. We're just excluding things so far. Here's one example. You have a beautiful star here in POS1, POS2, not seen. This is Sloan, PanStarrs. It never is seen again. It was just seen for a brief moment, very, very long time ago, and never again. Here's another example. This is much, much fainter. Here is our 20th magnitude. 1 star here. We actually see it also in POS1, in POS2. I haven't included a blue image from POS2 where it's also faintly, faintly seen. It seems to be a slight movement. You never find it again in the Sloan or PanStarrs. So this was also one of the more interesting cases we had. And you find more of these cases, just even if one tries to, like this one, never appears again. This one never appears again. This one never appears again. And we find 100 of these type of objects that are like of all kind of magnitude range, magnitude ranges. What we are doing now is that I'm getting help from a group in Ukraine that are experts on old photographic plates and to remeasure the magnitudes of all these objects. Because if I just try to, I've briefly done it myself, try to look at it, and it looks like these things are varying more than 8 or 9 magnitudes, some of them. And then you start wondering, what is this M-dwarf flares? Is it something else, or what are these things? Of course, one gets curious. However, while we are doing the follow-up, we're also following up with the rest of the images, because we only looked at 15% of the images we have in our sample. And this is actually a cross-disciplinary project with the IT researchers at Uppsala University. So what they have decided to help us with is to do this big data analysis, like the cross-matching processes. Difficult to do on a small laptop. They are helping us with this. They have a big cluster, and they're also going to help us with the image analysis. They have built a computational infrastructure that is built on that you have these candidates, and you try to, you have users that will try to help us with the analysis. so that we don't have to do it ourselves. They have proposed a machine learning solution where a machine learns which of the candidates are the most interesting, which of these candidates that could be kind of that one would be able to identify visually, because these 150,000 mismatches are based on catalogues, and then we have all these errors that we need to clean up. And we hope that the machine learning can help us to clean away all these uninteresting cases first, so that we don't have to do it ourselves, because it's a painful thing to go to do it all visually. So they built something called ML Blink, where the idea is to have citizen scientists matching images, and the machine is learning which of the candidates seem to be most interesting, and proposing these candidates to the user, and always updating the solution with the help of people who help to look through the things, so that we can get rid of all the artifacts the most efficient way. So this is one of the options we are looking into the most. And where are we now? Well, we are keeping on with cross-matching processes, because we want more candidates, and we want to do finer cross-matches where we solve the proper motion in different ways. And we are now in the progress of trying to find ways of analyzing the rest of the images, as I mentioned. And there will soon be, and we are trying to finalize the publication for this machine learning, ML Blink, this machine learning tool that will help us to identify the images. So this is where we are now, and of course with a follow-up. And so what do we hope that is going to lead us to? Well, we are interested, as I said, we are of course interested into the ET, but also generally into the exotic universe. We hope to find some really weird variable objects. We hope to find maybe the hypothetical failed supernova, even if it's not super likely. And we wish to find some rare or exotic or bizarre astrophysical phenomena that really need this 70 years or 100 years of time window. But we don't know if we will, but this is what we aim for. And yes, this is our goal. With this, I also wanted to mention that if for people who are interested into technosignature research at the EVAS in 2020, we are going to organize a symposium for technosignature searches that is open for everybody who are interested. And with this, I leave you. Thank you.
So now we have time for some questions. So, someone? Okay.
It's a very interesting exercise. So, but this is more a comment than a question. So, like 3 years ago, 4 years ago or so, we also found a transient in one of these USNO plates. We were studying a particular galaxy, and there was something there in the old place that went away. Something similar to what you have shown. No, we studied a thing in some detail, discarding everything possible, like from supernova to blue variable stars to, I mean, all the things that you can imagine. And we came up with an idea, which you hadn't mentioned there, but it's extremely exciting. Is the fact of lensing by primordial black holes in the halo of the Milky Way. So this is really the solution that we published in a paper 1 year ago or so, Philo et al. 2018, I think only notices. So I mean, lensing is another possibility for you to have these transients very short-lived. And the scales are such, and the time scales are such, years or so, that lensing by primordial black holes is one of the possibilities that you can have in mind. Yeah.
What's one of the time scales again, or that looks under transiting?
I mean, it was in one of the USNO plates. So you mentioned is, I mean, I think it was in the old ones. I don't have exactly the numbers, and so it did not appear in the next one, which is 20 years later or so, and it's not in the.
That's extremely exciting. Yeah, I will be happy to chat more about it.
Yeah, I mean, it's something similar, but it's lensing by black holes. Okay. No, it's a year stuff. It's I mean the best solution was in the halo of the Milky Way. I think it was like 4 kpcs in the halo or something like that, and so the time scale for the transients would be years, like 10 years or so.
Then that cannot be the same thing, because in some of the images I looked at them and there was an image taken maybe 2 hours later and nothing was seen.
So it was taken.
Ours are very shorter. There must be like minutes. More minutes.
But the plates that are available are taken 1950s,
Yes,
and then the next
sometimes-
ones.
Sometimes there's the red plate and the blue plates taken with maybe a few hours of difference, and then you look at it and you only find it in the red plate. You don't find
So
it.
then I'm talking about something else, because I think it showed up in both, in red and blue, and then went away 20 years later.
Oh, okay. Then ours went away much faster.
Okay. But
Surveys, modern surveys like Stripe 82, where you have observed the same region of the sky 80 times during 5 years, it would be a perfect place to look for the things that you are saying, because I mean, you have the same instruments, so you know the systematics, and then you just look for 5 years.
Lensing is still viable. It does not have to be a black hole. So it depends. Yeah, in your case, but in that case, yes. But the time scale of the lensing depends on the mass of the object. So if the time scale is very short, then it cannot be a black hole, but it could be a free-floating planet or something like that. So the time lensing is still a very good possibility that should be mentioned, I think. Yeah. Okay. I would like to comment that if you think your main contribution to candidates could be M dwarfs, flares of M dwarfs, it's a likely possibility because they are so common and they have strong flares. Recently, we saw a spectacular one in the Havalambre survey. It's not published yet, but it's several magnitudes going off. But perhaps I see that you are only looking in the optical. There are also deep infrared surveys, and these objects could show up in the infrared. So if you look at even an M dwarf that flares, there could be a counterpart in the in.
We haven't found them yet. We have already looked a little bit in other catalogues also to approximate these things with other catalogues. We haven't found any counterparts yet.
In the infrared, you look at WISE, you look at UKIDS. Okay, because you didn't mention that, so I was thinking that. Yeah, you mentioned only optical catalogs.
Well, Vizier, if you look in Vizier, it includes all the infrared and everything, so you get directly, you can check, and we have already looked one of them that shows up in any of the other catalogues, and all the ones are not shown up. They are not in any characteristic variable catalogues either. They are just not caught up by this year. They must be so faint if they are. We probably caught the bright state. Maybe it's end worst, or some very, very faint end worst. But it's very likely that they are.
When you are looking for infrared counterparts, you are using Visier.
I can use Visier as well.
Huh?
I can use Visier as well.
Yes, but is that what you are using? You are not.
We have done that, yes.
Hmm?
So far, we have only done it with Visier because it's
Okay.
the simplest, quickest one.
Okay. Okay, but you may estimate what could be the brightness in the infrared. So it could be faint, but still some deep surveys may be able to detect it. But I am not sure that they will be in BCR though. So you may have to actually go to the survey like Vista, like to the deep part, to the faint objects, and check, because there are not so many. So perhaps you really need to go to the deep
It's
image.
for the 2016 object, and it wasn't visible at all that day, for instance. We checked in WISE and 2MASS, and nothing was.
No, 2MASS is too shallow.
Too faint.
2MASS is too shallow.
Yeah,
No,
but
you have to go to Vista, you have to go to UKIDS, and
we will see. We find it's a good idea.
Is there any?
Yeah, it's also a kind of follow-up of another data set that you might want to have a look is either the Kepler or the TESS data set. If you are certain that at least some of these candidates are flares from M dwarfs, these data sets are optical, and you have like 90 days of coverage. And in that case, you might expect to also observe some flares, even if you don't see the target directly. So you could try of those 100 candidates, which ones are in the Kepler field or in one of the K2 fields, or in the test field, so that you get one image every 30 minutes of the whole test field, which will be the whole sky in short time. So that's a suggestion. Okay.
I'll have time for another question if there is. No?
It's completely different from what I said before. It's about this wow signal, this famous wow signal. So could it be a fast radio burst or no? Because we now know that they are kind of common.
But one didn't know it in those times.
Yeah.
I don't know the answer to this question, to be honest. But I think the point is, the wow signal was an unfound thing, so I don't know, I doubt the conclusion of I think it's more likely that this was someone, well, maybe they were not lost in those times, but there's so much of interference that we can have this there, and it's difficult to pinpoint what which direction it is.
You know that fast radio burst sometimes because people thought that it was a microwave in the kitchen of the observatory, but it was leaking into the signals.
I remember that one, that paper.
So thank you so much for the talk, Beatriz, and everyone for coming today.